Okay, we're going to continue on with our VFA absorption and management. We talked some on the lecture just as we left for break, and we'll talk a little bit more getting into the specifics of how VFAs are moved through in the coming week. But we're going to take that next step. This part is probably the most complex portion of what we're trying to do this semester. This is probably the heaviest and toughest concept to grasp. So this is probably as deep as we're going to go into physiology, and then the rest we're going to kind of back out and get more practice. So you've seen this before. We have the rumen over here, the luminal side. This is where you stuck your hand in when you did the rumen dive, rumen dump. We've got the lining of the rumen epithelium, and then we've got the blood and rest of the body over here. What we really want to focus on, here's our electrolytes going through, but our focus is on the ability of sodium to get through. So we have an active transport here, an active transport here. We're going down our concentration gradient here through a channel, and then sodium gets over here. Chloride can go as well. Potassium has two different ways, but we know sodium comes in with sodium bicarb, and its ability to cross over becomes very important. So, Natalie, you've had this before. Haley, you haven't. Well, you may have had it, but not in my classes. I'm doing it in A&P next week. So we've got the Henderson-Hasselbalch equation. We have the ability of carbon dioxide and water generated in the body from metabolism, more or less ubiquitous in the body. We have a carbonic anhydrase that's going to create our carbonic acid here, which will very quickly dissociate into our acid and our bicarbonate unit over here. So this reaction occurs everywhere in the body. These we consider more or less an excess. These are limited in their appearance. This is non-existent because if it's here, it's going to immediately go to there. Or if there's a mass action thing, it's going to force it back that way. So it's a key reaction in the lungs, the kidneys, the cells, and what we're going to focus here, at least to get started, is on the rumen and the ruminal lining. So we need to get the VFAs from the rumen over to the blood side. So there's two ways we can think about that. One is we have the VFA that still has its proton on it. Most of the time in the rumen, 90% of our acid or VFAs are associated. The pH is such that they're going to take that. Nope, it's the other way around. They are usually unassociated, but about 10% are unassociated. So they still have their proton on. They are fat soluble, lipid soluble. They will pass through a membrane without any problem. Once they are in, this is 6 pH. Once they are in the 7 pH of the cell, they're going to immediately dissociate. There's 100 times more likely to do that inside the cell. So you have a negatively charged VFA, and then you've got this proton that has to be managed. The proton is dangerous to the cell. It's going to rip it apart. You have this active transport we've talked about before that's going to pump that proton out in exchange for a positive charge. This positive charge balances the negative charge, and there's no pH effect in the ruminal epithelium. Where does that sodium come from? That comes from the bicarb. We have the proton combining with those two as they build up. They're going to create that carbonic acid, and you're going to hide that proton in the water. It's going to dissociate like bubbles coming out of a soda can. You're going to have the CO2 and water broken down there. So you're hiding the proton that's dangerous to the body in water for the short run. So this is when the acid or the VFA is associated. if we deal with the 1 and 90% of the VFAs are dissociated, we're going to have that VFA there. We've got a negative charge. We're going to have a transporter that's going to take it across the membrane in exchange for a bicarb. So you've got charge balance, so negative goes in and negative goes out. And then that gets us there. And again, we're going to balance that with the sodium on the other side. Now you've got, when you disassociate in the rumen, you've got the associated form. It dissociates. 90% of the VFAs are dissociated in the rumen. You could take that bicarb that was exchanged out here, take that proton, they go to carbonic acid and CO2 and water. So again, you're hiding that proton in water. Bicarb comes down. You've got it dissociated, a negative and a positive. The positive goes in, exchanged for a proton comes out. So positive exchange for a positive. You've got that bicarb coming down. You've got the proton coming out. The hydrogen ion, again, carbonic acid, CO2, and water. So we're putting those things there. Now in the cell, you've got lots of CO2 because the cell is alive. It's generating CO2. There's lots of water in the cell. We talk about 45% of the body water is in cells, and you're looking at probably 90% water in cells, depending on where you are and what's going on. That's going to run the reaction backgrounds. The carbonic anhydrase in the cells going to generate that carbonic acid that's going to immediately dissociate into the parts, and you have basically the carbonic acid being moved outside, regenerated back to CO2 and water. So you see the method going there, you're going to regenerate. With the active transport, you've now gotten a sodium across and a negatively charged VFA across, and they are in the cell. A little bit more complicated, but again, you're balancing the charges. You're making sure everything works. So when we think about what we're trying to achieve here, we're moving that VFA across from negatively charged, potentially, certainly negatively charged in the cell, and we want it to get to the blood, a negative charge. The sodium coming from the saliva is going to be moved across in an active transport. It's going to be worked out, moved out with that sodium potassium ATP ACE pump. So you have a charge balance, a negative with a positive, and you have something that's not going to generate acid in the blood. The animal's going to be protected. And you're hiding that hydrogen ion that's associated with that in water. So what we have here is kind of a dance. You have your sodium and your bicarb. They come from the saliva. They come down to buffer the rumen. And then you have your VFA and its proton. When it's a volatile fatty acid, it still has a dissociate. We got lactate, acetate, propionate, butyrate, and it's given up its hydrogen ion. We can have these two there. So this is what we have generated in the rumen, generated from the saliva. We do the dance, we do-si-do, we trade partners. This becomes carbonic acid, which goes to CO2 and water. And this becomes the management of that VFA as it moves through the body. And we don't have that acid proton that's going to throw off our body and give us acidosis, at least we. So if we make some assumptions, osmolality, what we have in the rumen is a function of the sodium present, which is fairly high. Potassium chloride, not so much. And then the VFA, which is fairly high. So most of the osmolality in the rumen is from the sodium and the VFA. If we look at all the things that we're going to do in this cycle, the bicarb, the VFA, the hydrogen ion, They all can be created and destroyed by either microbial means or by the cow's body doing that. Sodium remains constant. Sodium as an ion cannot be changed unless you have a nuclear reactor. So in the body, sodium is always sodium. It can never be broken down. It can never be turned into anything else. Sodium is always sodium. Another thing to remember is when we think about DCAD, we have our sodium, potassium, our positive charges. We're minusing our chloride and sulfur. Dry cows, we want our sodium, potassium to be less than or equal to our sulfur and chloride in our feed. And in lactating, we actually want the sodium, potassium to be a little bit greater than the chloride and sulfur. You want something on the positive side. Cow seems to do well about 45 milliequivalents per 100 grams during lactation, and that's probably a function of their uh, management of a very large acid load. We don't have as much of an acid load, and we're also trying to get the bones to pull out calcium. So we bring this acidosis, generate this acidosis. When you have the negative charge, they create acid in the blood. The positive charge create base. So we think about base versus acid. We can balance things out. So here's what we need to think about, and here's probably the most complicated thing I'm going to teach. We have our model of a cow here. We have the salivary gland. We have the rumen, and then the surrounding tissues, blood, tissues. We have metabolism out in the body, and we have our carbonic anhydrase in the body. And those are going to be important players as we generate a cycle through these three compartments. So let's start with the blood. We have sodium bicarb in the blood. You have lots of sodium in the blood, 150 milliequivalents, 140 milliequivalents. And then bicarb will be generated, but you have, as they go into the salivary gland together. And from there, that sodium is going to move into the rumen. So and the bicarb is going to go there. We know that once that bicarb gets into the rumen, it's going to find any loose protons and it's going to be turned over to CO2 and water. The sodium remains constant. We've got the cycle. We talked about the VFA. It's going to generate that hydrogen. Either that hydrogen is going to go out into the epithelium and come back, but it's always going to, or it's going to go directly into carbonic acid and CO2 and water. We're going to hide that hydrogen ion in water. So we're going to have a net moving the VFA, our negatively charged, out into the body. We're missing our sodium here. Sodium is going to move in parallel with that negative charge. So if we look at our sodium, it's going to be more or less constant going through. It's going to move from the blood to the salivary gland to the rumen back to the blood. It's going to go more or less in a cycle. You're going to have your VFA. It's going to go out into the body. As it's metabolized, as part of its metabolism, it needs to get its hydrogen proton back for the equation balance. And with that, the carbonic anhydrase is going to regenerate that proton, take the CO2 and water, break it apart, give the proton back to the VFA that's going to be metabolized to CO2 and water. And then what's left over is the bicarb. So as the VFA is destroyed, the bicarb is regenerated. VFA takes back its proton from the carbonic acid, and we leave behind the bicarb. So you have this cycle going around. of these two things. The sodium remains constant, the bicarb gets into the rumen, becomes CO2 and water. That negative charge moves over to the VFA, goes out, is metabolized. That proton goes back. What's kicked out is the bicarb. So you have this cycle going through the body. So if we think about it, sodium seems to be a very important player in the management of acid, the VFA in the body. We're talking about a very heavy acid load on the cow each day, 70 equivalents of acid. That's a huge load. Her ability to process that, her ability to manage that, really, I think, comes back to her ability with sodium. I think this is the reason that if cows get acidosis, they tend to start to hit the bicarb. They need some sodium to get the job done. So adding to this pool, adding into the rumen, that's why I think they hit it. Is that the real thing? I don't know. We don't know. Nobody's ever going to pay for that study, but that's what I think. So that's my theory. This is basically from my dissertation. Sodium is a big player there. It never changes, so it's always a good placeholder moving through. And then you've got the transition back and forth where you're protecting the body from that proton by this dance, that do-si-do, and we hide it and then bring it back as we regenerate the bicarb.